Welcome back to Physics 142. In this video, I want to think a little bit more about the concept of resistance and what we can learn about resistance in wires. So, first of all, last video we talked about resistance as being a change in potential divided by current. Right? However much energy you lose flowing through a wire per amount of energy flow, that's our definition of resistance. Now, the more common way that this often will get represented is that people will take and multiply this I over and write that I times R equals V equals the change in potential. This gets a special name. It's called Ohm's law. But I just want to point out one specific caution that Ohm's law actually only applies sometimes. And so what do I mean by that? Well, what I'd like to do is I'd like to think about a couple of plots. I'd like to think about a plot of potential versus current. All right, this is a plot of potential versus current for some device. And if we look at Ohm's law here, what do we expect this plot to look like? Well, plotting current versus potential, we would expect to have a linear relationship, right? Where the slope, I guess, if I have current on the y-axis, and y would equal 1 over r times v, right? So the slope here would be 1 over r, right? The slope would be 1 over r. And this is sort of what we expect for Ohm's law. And for a lot of devices, if you make a plot of I versus V, so the current at a bunch of different potentials, you'll see that you'll actually get this nice linear relationship. If you get this linear relationship, we call this an ohmic device. And basically here, what we're saying is that the resistance is independent of the potential that you apply, right? That the slope is the same no matter what the potential is here. This is an ohmic device. But the thing is, not all devices are ohmic devices. So if instead I wanted to make a graph for some other circuit elements, like for example, a circuit element like a diode is a special kind of circuit element. If you make this graph for a diode, what you'll see is that you don't get a linear relationship. You actually get something that looks a little bit more like that, where the resistance is different, the slope is different for different voltages. All right, so this would be a non-ohmic device. Now, most of the systems and devices that we'll encounter in this class will be able to assume Ohm's law. We'll be able to assume this is a linear relationship. But I just want to call your attention to the fact that this is not true for all devices. And so we do need to be careful using this formula, that we are using it just for things that are ohmic devices. If you have a non-ohmic device, then you need to think about just little pieces, right? You need to break this up into, little pieces and think about the derivative in this function to think about resistance. So, all right, so that's the difference between ohmic and non-ohmic devices, and just a good thing to be aware of. There's one other sort of property of resistors that's good to be aware of, and specifically, you might think, when we think about resistance, we think a lot about resistance in, say, wires. And so it'd be nice to know how resistance depends not just on the current and the potential in a circuit, but on the actual properties of a specific wire. And the answer is that we actually can quantify that we do have a way of quantifying that. All right, so let's think now about how resistance might depend on actual physical properties of some wire. And well, if we think about it, All right, clearly the resistance is going to depend on what kind of material we have. If we have some sort of conductor, then it will have very low resistance, right? Current will flow through it really easily without losing very much energy, as opposed to for more insulating materials, we expect to have a lot of resistance, right? Current won't want to flow through it very easily. So we quantify sort of the amount that an object is a conductor versus an insulator using letter rho. And rho here is something we call the resistivity. The resistivity, all right? And the resistivity is something you look up in sort of a table. It depends specifically on the material. So it depends on the material. And it also depends on temperature. So that's a good thing to be aware of. But the resistance in a wire, turns out, isn't just dependent on the material, but there's a couple other properties that it's dependent on. Well, one thing that we want to think about is how long the wire is. Clearly, if you have a short wire, then you're going to lose less energy than if you have a really long wire, right? There's sort of more chance for the electrons to get scattered in a longer wire, so you get more resistance in a longer wire. So resistance also depends on the length of a wire here. So this is the length. And if you make L bigger, that will make the resistance bigger, right? If you make the length bigger, the resistance should get bigger. But it also ends up depending on how thick your wire is, what the cross-sectional area of the wire is. The cross-sectional area. And the way to think about this is to maybe think about it sort of like a pipe or something like that, all right? The wider you make a pipe, the more water can flow through it, right? So similarly, the thicker you make the wire, the larger you make the cross-sectional area. What do we mean by that? Well, if, here's some wire, cross-sectional area is just a slice right through it, right? Slice right through right there. That would be the cross-sectional area of the wire. And the bigger you make it, the thicker you make the wire, the easier it is for current to flow. And so that makes the resistance go down. So this formula right here, R equals rho L over A, is another way of talking about resistance and specifically relating resistance to the properties of a wire. It might be useful if I did one quick example of this. So maybe as an example, let's think about a 50-meter ohmic copper wire. I guess let's use some sig figs. A 50-meter ohmic copper wire. And copper, if we go and look in a table, has a rho, a resistivity of about 1.72 times 10 to the minus 8 ohm meters. All right. So that's the resistivity there. And let's say our wire has a cross-sectional area of 8.2 times 10 to the minus 7 square meters, right? Wires are pretty small if you actually put them in units of square meters, but I'll save the unit conversion for us here. All right, so 8.2 times 10 to the minus 7 square meters. And let's connect this wire here across a battery that has, let's say our battery has a potential of 1.75 volts. All right, so we're going to connect our wire across a 1.75 volt battery. And the questions I want to ask are, what is the resistance in our circuit? And what is the current that flows through our wire? So find R and I. All right, there is sort of our question. So how do we approach this? Well, there's two important formulas. This V equals I times R, and R equals rho L over A. All right, clearly we know rho. We know L and we know A, so we can combine all of those numbers. So we could write this down. R equals rho L over A, which is going to be 1.72 times 10 to the minus 8 ohm meters, all right, times 50 meters divided by 8.2 times 10 to the minus 7 meters. And when you plug all that into a calculator, I got that it comes out to 1.05 ohms. So that would be the resistance of our wire. And so now that I know the resistance and I know the potential across the battery, I can also find the current. And specifically rearranging this formula, solving for I get that I equals V over R. So that will just be 1.75 volts divided by 1.05 ohms. And that's going to come out to 1.67 amps worth of current. So there you have it. You know, these formulas, we can nicely use them together and calculate all of these different quantities, how much potential we have across our circuit, the resistance in the circuit, and how much current is flowing through our circuit.